everyone, this is Dr. Nak and we're about to learn how to use radicals in functions. So what's a radical function? Well, a radical function is just a function that's defined by a radical expression. For instance, radical, let's just give a maybe cube root of x. So this is a radical expression, isn't it? But we're going to express this as a function, so all we're going to do is just name this guy f of x. And that's pretty much it. Let's do some examples. Example 1, let f of x to be square root of 2x minus 1. And the question is find f of 5 and f of negative 2. Alright, so let's do this. So when x is 5, so we're going to call it f of 5. What is the corresponding y value? Well, y value is the output of f of 5. So here you're going to have 2 times 5 minus 1. So that's going to be 10 minus 1. And square root of 9. And answer is 3. So we say that when x is 5, corresponding y value is 3. Now let's take a look at f of negative 2. Okay, we're going to do the same thing. So we got 2 times negative 2 minus 1. So here what we're going to get is negative 4 minus 1, which is the square root of negative 5. Square root of a negative? That cannot happen. So in this case, our answer is going to be not a real number, or we can say that the function does not have a value at x equals to negative 2. But let me write this answer as not a real number. Let's take a look at another one. Example 2, let g of x to be cube root of 5x minus 2. Find g of 2 and g of negative 5. Alright, so let's first start out with g of 2. So when x equals to 2, what is our corresponding y value? Well, let's compute. So here you're going to have the cube root of 5 times 2 minus 2, which gives us the cube root of 10 minus 2. Alright, which is cube root of 8. Now remember, you need to simplify your radicals all the way. So, looks like 8 is 2 to the third. So this can be written as cube root of 2 to the third. So our answer is going to be 2. Now let's take a look at g of negative 5. We're going to do the same thing. So we got cube root of 5 times negative 5 minus 2. So this is going to be cube root of negative 25 minus 2, which is going to be cube root of minus 27. And if I want to break down the 27, I'm going to go 3 times 9, and then 3. Excellent. We got perfect cube. So now this becomes, let me just write it over here, cube root of negative 3 to the third. Now remember, this time you're given the cube root, so you can have a negative number inside of the radical. So in this case, our answer is just going to be negative 3, because the power of 3 and the cube root, they're going to cancel each other out. So our answer is negative 3. So let's go back and review the properties of nth root of a. Now, if n is even, for example, maybe square root or fourth root, nth root of a is defined for all a that are greater or equal to 0, which means that if n is even, nth root of a negative number is going to become undefined, which also tells us that the domain of nth root of a when n is even is set of all a values such that a must be greater or equal to 0. Basically, if you're given the nth root, whoever sits under the radical must be greater or equal to 0 no matter what. Now the second case is if n is odd, for example cube root or fifth root, nth root of a is defined for all values of a. So there's no restriction on the radicand. So in this case, a can be positive, a can be 0, or a can be negative. So in this case, the domain of nth root of a, if n is odd, it's going to be settable a values such that, that bar means such that a is all real numbers. Okay, now let's take a look at some examples involving the domain of a function. So example 2, find the domain of f of x equals square root of 3x minus 4. So notice here that we're given the square root, which means that n is even. So the restriction is that whoever sits inside of the radical must be greater or equal to 0 no matter what. So that's going to be the restriction. So here what I'm going to do is I'm going to start out with the restriction, which will be 3x minus 4 must be always positive. So all you have to do is solve for x from there. So I'm going to add 4. Looks like we're going to have 3x is greater or equal to 4 dividing by 3. I'm going to go over here. So this implies that restriction on the x must be x better be greater or equal to 4/3. Now, let's express this answer in a set builder notation and also in an interval notation. So, but before, let me just box that because that's important. So on the set builder notation, you will answer it as the domain of f is settable x values such that, again, that bar means such that, x must be greater or equal to 4/3. Now let's go with the interval notation. So to me, interval notation is easier for me to write if I draw this situation in number line. So this is my 4/3, infinity, negative infinity. Now x is going to be greater or equal to 4/3. So here's my close bracket. And I'm going to be shading all the way up to positive infinity. So in the interval notation, I'm just going to write it as int. Our answer here is going to be 4/3 all the way up to infinity. So here is the domain in a set builder notation. I usually just call it a set notation. And then here is the answer for the interval notation. So this is basically telling you that if you plug it in any number that are greater or equal to 4/3, our square root value will be defined. So for instance, let me just pick something that's less than 4/3. So how about like maybe a 0? So notice that 0 is outside of the domain. So because 0 is right here. So this guy is outside of the domain. Okay, so now let's see what's going to happen if I plug that 0 into the function. So if I go f of 0, when x is 0, here what we're going to get is 3 times 0 minus 4. What are we going to get here? We're going to have a square root of a negative, which we cannot have. So the domain basically tells you, all right, what value of x can I plug it in so that the function will still be defined? Well, our answer is that you can plug it in any number that are greater or equal to 4/3, then our function f of x will be defined. Let's take a look at another one. Let's find the domain of g of x, which is going to be 4th root of 4 minus 5x. So again, here we're given the eventh root. So our restriction is that whoever sits inside of the radical must be greater or equal to 0. All right, so now I'm going to write down the restriction. And all we have to do is solve for x. So I'm going to subtract 4. Then here you're going to have negative 5x is greater or equal to negative 4. Now I'm going to be dividing by negative, divided by negative. Do you remember what's going to happen? Yes, your inequality sign switches when you divide it by a negative. I don't know why I wrote that inequality so big, but oh well. So here you're going to have x is less than or equal to negative 4/3 over, not negative 4/3, I'm sorry, negative 4 over negative 5 is positive 4/5. All right, so in a set builder notation, our domain of G is going to be set of all x values such that. x must be less than or equal to 4/5. Okay, now to get the interval notation, I'm just gonna draw the picture. All right, so this is telling me x is less than or equal to 4/5. So I'm gonna shade this side and I'm gonna translate it directly below. So here we're gonna have open negative infinity to 4/5 closed. So that's gonna be the domain of our g of x. And what the heck, let's just look at the odd root. So let's find the domain of cube root of x minus 5. Okay, now since we're given the odd root, which is a cube root, well, are there any restriction under the radical? No. So if you're given like maybe cube root or fifth root, you don't have to do anything. So all you have to do is the domain of h is all real numbers and be done with it. All right, so domain of h is a settable x values such that x is all real numbers. Okay, now how do you translate that in an interval notation? Well, it's defined for all real numbers. So here's negative infinity to positive infinity. It's defined for any value of x. So in this case, to express that, answer is going to be from negative infinity to positive infinity. That tells you that domain is going to be all real numbers. So I'm just going to box those two. All right, now let's take a look at something like this. Find the domain of f of x equals square root of 6 over x minus 1. Do you notice any difference between this problem and the previous problems that we did? Yep, we got the fraction going on inside of the radical. So that will be the only difference. But let's take this step by step. Okay, so first of all, since we're given the square root, restriction is that whoever sits inside of that square root must be greater or equal to 0. So first, I'm going to write that restriction. Okay, so first restriction will be 6 over x minus 1 must be greater or equal to 0. All right, now do you see the second restriction on this? Well, can you ever have a 0 on the bottom of the fraction? Answer is no. So in this case, there's going to be a second restriction. Second restriction is that bottom of the fraction cannot be 0. So we're going to have to go x minus 1, that's the denominator, that's the bottom, cannot be 0. All right, so those are the two restrictions that we're going to get. Okay, so first, let me just solve for circle 2's might be easier. So here, this implies that x cannot equal to 1. So I'm going to box that. All right, now let's look at the first restriction. We have 6 over x minus 1 must be greater or equal to 0. Well, greater or equal to 0 means that 6 over x minus 1 must be positive. Okay, so there are a couple ways that you can think of it, but notice that in order for the fractions to be positive, either top is positive and the bottom is positive, because positive over positive is positive, or top and the bottom both must be negative, because negative over negative is a positive. All right, so in this case, but the thing is, this guy is a positive number. Okay, so in order for the fractions to be positive, do you see that the bottom also must be positive? Because then we're going to have positive over positive will be greater or equal to 0, which means that it's going to be positive. All right, so with that said, in order for the bottom to become positive, we're going to have to set that as the bottom, which is x minus 1, must be greater or equal to 0. So that tells me that the bottom is going to be positive. So let's solve for such x. So if I solve for such x, we're just going to be adding 1 to both of them. So here what we're going to get is x is greater or equal to 1. All right, so let me box that. Now what we need to do is we're going to have to analyze these two restrictions together. All right, so the restrictions are x must be greater or equal to 1, but at the same time, x cannot be 1. So let me draw this out on a number line. So suppose this is 1, infinity, negative infinity. Well, x must be greater or equal to 1, so that will be like that. But the thing is, x cannot be 1. So do you see that here we're going to have an open circle or open parentheses around 1. So in this case, if I combine those two restrictions together, the domain is going to be open 1 to positive infinity. Did you get that part okay? Don't worry, we're going to do another example. But so this is going to be an interval notation. Now the set notation will be the domain of f is going to be settable x values such that, well, all the x must be strictly greater than 1. So I'm going to box this for the interval notation, and this is for the set builder notation for the answer. Let's do another one that looks kind of similar to part A. G of x equals square root of 9 over 5 minus x. So again, we want to find the domain of this function. So let's do the same thing. So we got fractions going on here. So first restriction is that whoever sits inside of the square root, which is the eventh root, must be greater or equal to 0. So I'm going to write down the first restriction. So here you're going to have 9 over 5 minus x must be greater or equal to 0. Now since we're given a fraction, notice that again, there's going to be a second restriction, which will be that the bottom of the fraction cannot be 0. So in this case, second restriction will be 5 minus x cannot be 0. All right, so now let's solve for, to me, circle 2 is much easier, so let me just do that. So here I'm going to subtract 5, or I guess I could add the x on both sides, huh? So let me just go add x. So here we're going to have x cannot be 5. Okay, let me box that. Now let's deal with the first restriction. First restriction says that 9 over 5 minus x must be greater or equal to 0, which means that it must be positive. So again, notice that 9 is positive. All right, now if the fraction is going to be positive, we better have positive over positive or negative over a negative. But in this case, since top is a positive 9, what needs to happen is that this guy must be positive. I'm just going to write it as plus, denotes as positive. So let's write that out. So here, another restriction is going to be 5 minus x better be greater or equal to 0, which is same thing as 5 minus x must be positive. All right, so then let me just add x. Then here you're going to have 5 is greater or equal to x. Well, let me just rewrite it so that way x, the variable, is going to be on the left. So this is same thing as x is going to be less than or equal to 5. Because look, the inequality, the bigger side is facing 5, isn't it? So in that case, bigger side, when you swap the inequality, the bigger side also better be facing the 5. All right, so I think I just made a mess right there, but hopefully you can read that. But anyways, let me box that. Now let's analyze the situations here. Okay, so this is telling us that the domain is going to be settable x values such that x must be less than or equal to 5, but all at the same time, x cannot be 5. So just gonna draw the situation out. So here is 5. Well, x cannot be 5, so let me just take care of that one first. So x cannot be 5. So I'm gonna have an open circle here, which indicates that 5 is not included. And then x is less than or equal to 5, so I'm gonna be shading x is less than 5. So in this case, our answer is gonna be negative infinity to 5 open, because look, if I plugged it in 5 inside of our function g of x, do you see that you're going to have square root of 9 minus 5 minus 5, which is 9 over 0, which becomes undefined. Okay, so now let's express this in the set notation. So the domain of G, it's going to be settable x values such that, well, all the x values are, in this case, less than, strictly less than 5. So I'm going to box these two for the answer. How you guys doing? Maybe we should do another example just to see if you can do it or not. All right, let's do another one. All right, so I want you to pause the video and try this problem on your own. The question is, find the domain of h of x. And again, I'm pausing. I don't know why every time I say pause the video and then I pause myself. But anyways, all right, so what I'm going to do is I'm going to start working on this. So again, we're given the square root, so whoever sits inside must be greater or equal to 0. So that's going to be our first restriction. All right, now what's the second restriction? Well, we could never have a 0 on the bottom of the fraction bar. So in this case, the denominator cannot be 0. Okay, so I think we're good to go. So this implies that x cannot be negative 3. And again, let's analyze. So in this case, notice that top is positive. Good to go. So that means what then? The bottom must be positive. Oops. So then we're going to have positive over positive is going to be greater or equal to 0, which means positive no matter what. All right, so now I'm going to combine these two. Oh, wait a minute. I haven't answered that portion yet. So this means that x plus 3 must be greater or equal to 0. So that means x better be greater or equal to negative 3. All right, now I'm going to combine these two together. So here's negative infinity, positive infinity, negative 3. All right, so first of all, x cannot be negative 3. So I'm going to have an open circle around that to indicate that negative 3 cannot be included as a part of the domain. And here you're going to have x is greater or equal to negative 3. So in this case, we're going to be shading this side. All right, so now I'm going to translate that directly below to write the interval notation. So here you're going to have open negative 3 to positive infinity. So that's going to be the domain. And then I'm just going to write it as domain of h. It's going to be settable x values such that, well, all the x values are here. So notice that all the x values are strictly greater than negative 3. So this is our answer for the domain of h. How did you do on this one? Hopefully you're kind of getting hang of it. So let's take a look at something a little bit more involved next. Example 4, find the domain of f of x equals square root of x plus 3 over x minus 2. Now, what's the difference between example 3 and example 4? Well, we got variables on the numerator and also in the denominator for this one. Whereas for the previous one, we only saw the variable on the denominator. So that's the big difference between these two. Now, there are a couple ways that you can do this, but the way that made more sense to me is drawing this out on a number line, which I need to explain to you a little bit. But if you want to do this formally without the number line, first, what you need to do is, well, get all the restrictions out of there. So first of all, do you see that we cannot have 2 on the bottom? So x cannot be 2. So that will be the first restriction, because if x is 2, the fraction that becomes undefined because you're going to have a number over 0. So for the first restriction that I see is that x cannot be 2. All right. Now, second restriction for this will be that whoever sits inside of the square root, eventh root, must be greater or equal to 0. Correct? So here, x plus 3 over x minus 2 must be greater or equal to 0, which means this quotient has to be positive. All right, now from here, there are two cases. case 1 would be that both numerator and denominator must be positive. Or case 2 would be that the top and the bottom both must be negative, because positive over positive gives a positive value, and negative over negative will give us a positive value. So here, case 1 would be both positive. So let me write it as, well, x plus 3 must be greater or equal to 0, and x minus 2 must be greater or equal to 0. All right, so in this case, x better be greater or equal to negative 3, and x is greater or equal to 2. I just solved the inequalities here. All right, so that's one case. All right, now let's deal with case 2. Case 2 is that we better have negative over negative to make the quotient positive. So here we're going to have x plus 3 must be negative, less than or equal to 0, and at the same time, x minus 2 must be less than or equal to 0. So solving for x, here we're going to have x is less than or equal to negative 3, and x is less than or equal to 2. All right, so let me box this, and then let me just draw the picture here. So I'm going to draw the number line on the left. And so we got negative 3 and a 2 as a key point. So negative 3 and a 2. All right, so from case 1, x better be greater or equal to negative 3. So this is going to be going this way. All right, but at the same time, x better be greater or equal to 2, but with the restriction circle 1, x cannot be 2. So here, I'm going to have an open circle around 2, and then x better be greater or equal to 2. So in this case, what we're going to have to do is we're going to have to shade this portion. Since we're talking about the and, we must take the overlapping parts of the interval. So from case 1, the domain that we can get out of it is, well, where is it overlapping? It's overlapping from 2 to infinity. So here you're going to have open 2 to positive infinity. All right, so that's from case 1. Now let's go with case 2. I'm going to draw the number line again. So here's negative 3 and a 2. All right, x better be less than or equal to negative 3. All right, and at the same time, x must be less than or equal to 2, but the thing is, x cannot be 2. So I'm going to put an open circle, and x is less than or equal to 2, so we're going to have to be shading all the way down here. Now, since we have the word and in between, we're going to have to take the overlapping portion of the interval. So here, I forgot to write negative infinity and positive infinity. So here we're going to have negative infinity to negative 3 closed. So I'm just going to box that. So our answer is going to look like this. So our domain of f in the interval notation is going to be negative infinity to negative 3 closed, and then union open 2 to positive infinity. So this is going to be the official answer. Now, if you want to write this in the set notation, we write this as set of x such that, let me see, x is going to be less than or equal to negative 3 in this case, comma, and all the x must be strictly greater than 2. Yikes. All right, but anyways, this is going to be our official answer. All right, now let me show you another way to do it by drawing, a bunch of number lines. Not bunch, all I need is 3 number lines. So let's take a look at the same example. Find the domain of f of x. All right, so here, what we need to do is, first we need to notice that whoever sits inside of the eventh root must be greater or equal to 0. Okay, so that's the portion that we're looking for. We want to solve for x where that x plus 3 over x minus 2 must be greater or equal to 0. Okay, so let me note that. So what we want is where x plus 3 over x minus 2 is positive. Okay, so that's what we're looking for, keep in mind. Now what I'm going to do is draw 3 number lines. You'll see why in a minute. So let me just bust out one of them, second one, and then the third one. Again, this is negative infinity to positive infinity. Okay, now the first number line is reserved for x plus 3. Second one is x minus 2. And then the last one is our whole expression, x plus 3 over x minus 2. Now, remember what we're looking for. What we want is for this guy to be positive. Keep that in mind. All right, so step number 1, find the 0 of x plus 3. Meaning that if I set x plus 3 to be 0, what's the value of x? So basically here what I'm going to do is I'm going to set that to 0. And if I solve for x, we're going to have x is what? Negative 3. And we're going to do the same thing for x minus 2. We're going to find the 0 of x minus 2, which will be x is 2. Okay, so keep those points in mind. Now I'm going to jot down negative 3. I'm going to pretend that this is a number line here. So this is our negative 3. 2 is bigger than negative 3, so I'm just going to write 2 up in here. And on the bottom is x plus 3 over x minus 2. So I'm just going to jot down all the key points directly below. All right, now let's talk about this. So first restriction would be, since we're given the fraction, do you see that the bottom cannot be 0, right? So that implies that x cannot be 2. Keep that in mind. So that means that I better have an open parentheses around 2 no matter what. All right, so now let's look at the first number line. Do you see that negative 3 right there? Now, plug some number that's bigger than negative 3, so which means that I'm looking for what's going to happen in this region. All right, so what's bigger than negative 3? Like maybe 0. So maybe 0 is over here, isn't it? Okay, so if I plug that in 0 in place of x, we're going to have 0 plus 3, which is a positive 3. So in this case, do you also notice that if I plug in any number that's going to be bigger than negative 3, all those values are going to be positive no matter what. So here, all this side is going to become positive. If you don't believe me, just pick like 10. All right, 10 is in that region right there. So if I plug it in 10 in place of x, we're going to have 10 plus 3, which is 13, which is positive. And then let's plug it in something that's less than negative 3. So maybe like negative 5 or something like that. That's smaller, right? Now, if I plugged it in negative 5 into that x plus 3, we're going to have negative 5 plus 3, which is going to give us negative 2. So all the values on the left of negative 3 are going to be negative. So I'm just going to draw it like that. All right. So now we're going to do the same thing for the second number line. So we know for sure that x cannot be 2. That's why we have that open circle there. All right. Now let's plug it in some number that's bigger than 2. So let's just say 3. So 3 is like maybe right here, right? So on this region, if I plug that 3 into x minus 2, we're going to have 3 minus 2, which will give us positive 1. So this tells you that on the right hand side of 2, no matter what number that you're going to plug it in, our answer is going to be positive because we're looking at the function x minus 2. And then to the left, so let's pick maybe 0. So 0 is to the left of 2, isn't it? If I plugged it in 0 into x minus 2, we're going to have 0 minus 2, which is going to give us negative. So that's telling you that if you pick any number of left of 2, we're going to have a negative value. All right, now let's look at the bottom one. The bottom number line is for the combination of 2. X plus 3 over x minus 2. Now, what are we looking for? So let's go back to what we want. I wrote it down right here. What we want is that our quotient, which is, x plus 3, x minus 2 to be positive. This is what we wanted, isn't it? All right, so now what we're going to do is this. Let's analyze that number line. So if I look at the number line on the left of negative 3, let me change the color a little bit. So what I'm talking about is this region right here to the left of that. Do you see that we have a negative over a negative? We have both negatives, right? So do you see the negative over a negative? That's going to give us a positive value in here, because here's our negative and this is our negative. All right, now let's look at the region between negative 3 and a 2. So that's in this region right here. Look at the sign on the top. Sign on the top is positive, sign on the bottom is negative. So we have a positive over negative, so our result is going to be negative. We're going to do the same thing for 2 all the way up to infinity. Now let's look at the top line. Top line is positive, and then the bottom line is positive. So we have a positive over a positive, which is going to give us a positive value. So guess what? Do you notice something? Because we already computed the answer from the way we did it previously. Notice that we're looking for the x plus 3 over x minus 2 to be positive. This is what we're looking for. And the bottom line is for x plus 3 over x minus 2. So guess what? You just extract the positive portion on that bottom number line, and that's going to be the answer. So the answer is going to be from negative infinity to negative 3 closed, and then here you're going to have a union, and then here you're going to have open to positive infinity. So I don't know why u is more towards the left hand side of the interval, but let me just change that up. I don't like that look. So here we go. Isn't that the exact same answer that we got from the way we did it formally? But anyways, I just wanted to show you the way that it made kind of sense to me, and to me it was a lot more easier to compute it this way. So I just wanted to show you this method. And yes, I know you want to try another one, right? So what I want you to do is pause the video and let's try something like this. Find the domain of g of x. So if you want to try this on your own, please pause the video and just try it. And meanwhile, I'm just going to start off same thing. So since we're given the square root, whoever sits inside must be greater or equal to 0. So what we want is the region where x minus 1 over x plus 4 is positive. This is the region that we're looking for. So what I'm going to do is I'm going to use my number line because I like it that way a lot better. So here's negative infinity, positive infinity. So this is the line, number line for x minus 1. Next line is for x plus 4. And then finally, the bottom is x minus 1 dividing by x plus 4. Alright, so now I'm going to find the 0 of x minus 1. So I'm going to set that equal to 0 and solve for x. So we're going to have x equals to 1. Let's do the same thing for x plus 4. So our 0 for x plus 4 is negative 4. Okay, so now I'm going to jot this down on the number line. So here is 1. And negative 4 should be the left of that. So I'm just going to jot this guy as negative 4. And I'm just going to jot down negative 4 and then 1 onto that third line. Alright, now the first restriction is that, let's see, x plus 4 cannot be 0 because x plus 4 is on the denominator. So let's take care of that first. So that implies that x cannot be negative 4. So around negative 4, I'm going to have an open circle around it. All right, so now let's analyze the number line. So let's go with the first one, first number line. If I plugged it in any value of x that are bigger than 1, so the right hand side of 1, so let's just say 2, if I plug that 2 into x minus 1, do you see that this is all going to be positive? So that means that the left hand side is all going to be negative. All right, now let's look at the second number line. So if I plugged it in any value that's going to be greater than negative 4, well, 0 is greater than negative 4. If I plug that in, do you see that 0 plus 4 gives a positive 4? So here, on the right hand side of negative 4, we're all going to get a positive. And on the left, we're going to get negative. All right, now let's analyze together. So, all right, now on that left of 4, we have a negative over a negative. So that's going to give us positive. Now in the middle, which means that negative 4 to 1, we have a negative over a positive. So here you're going to have a negative. And then the last one, we have a positive over a positive. So we're going to have a positive. So we're done. So translate. Then here what we're going to get is negative infinity to negative 4 open in this case, because that region is positive. And do you see why we're looking for positive? Because what we want is right here. We want the last number line to be positive. All right, so that's the reason why I'm just choosing the positive portion of that last number line. And here we're going to have closed 1 and positive infinity. Connect those two intervals by the union, and hey, we're done. And I did not ask you to write this in the set builder notation, so as long as in this case, if you could give me the interval notation, that will be fabulous. Do y'all want to try another one? Yes, we do. All right. All right, so please find the domain of h of x by pausing the video. And meanwhile, I'm just going to start off the same way as we always do. Since we're given the fourth root, which is the eventh root, whoever sits inside of the radical has to be greater or equal to 0. So what we want is to find the region where 2 minus x over x plus 5 is positive. That's the region that we're looking for. Okay, so I'm going to start off with 3 number lines, just like what we did before. The first line is reserved for 2 minus x. Next one, x plus 5. And the last one, 2 minus x over x plus 5. Find the 0 of each. So if I set that equal to 0, our x is going to be 2. Because I just added x on both sides. Now, 0 of x plus 5 is x equals to negative 5. So I'm just going to jot those 2 points down. So negative 5 is on the left of 2. So let me just write 2, negative 5. And the last one, I'm just going to drop down those 2 key points. All right, so now let's go with the first restriction. All right, look at the fraction. So first of all, x cannot be negative 5. Because if so, then the bottom of the fraction becomes 0. So I'm just going to jot down the open circle around negative 5. Okay, so now let's look at the first number line. If I plugged it in any value that's going to be bigger than 2, let's just pick 5, let's just say, right? So I'm going to pick 5. Plug that 5 into here. Do we have a positive answer or a negative answer? We have a negative. So in this case, I'm just going to put a negative here, and the rest of it is going to be positive no matter what. All right, now let's look at the second number line. So let's plug it in some value that's going to be bigger than negative 5, which is 0. So if I plugged it in 0 into place of x, 0 plus 5 is positive. So here, we're going to have all positive. That means on the left of it is going to be negative. All right, now let's jot this down. All right, so we got positive over negative on the first region. So this is going to be negative. Now, between negative 5 and a 2, we have a positive over a positive, so this region's positive. And then the last one, what do you think? We have a negative over a positive, so this is going to be negative. Now, what are we looking for? We're looking for where the 2 minus x over x plus 5 is going to be positive. Okay, so translate that directly below and write your interval notation. Well, where is it positive? So in this case, only positive region is open negative 5 to 2 closed. So that's our final answer. Do you like this method? Well, I liked it a lot, especially this method helped me when I took this class for the 3rd time around. But anyways, I just wanted to share that with you. All right, now let's get into the next topic. Graphing radical functions. Now we're going to be graphing a radical function, and on top of it all, we have to determine the domain of that function. I know it sounds horrible, but it's not as bad as you think. All right, so let's do some examples. For f of x equals square root of x plus 3, let's find the domain. Then we're going to graph it. And from that graph, we're going to find the range of that function. All right, so let's first go with the domain. Domain of f. Okay, now what's the restriction? Hopefully you're kind of getting the hang of it. So since we're given the square root, whoever sits inside must be greater or equal to 0. So in this case, solving for x, we're going to have x must be greater or equal to negative 3. So in this case, domain of f in a set builder notation is going to be set of all x such that x must be greater or equal to negative 3. And in interval notation, it's going to be, this is same thing as closed negative 3 all the way up to positive infinity. So that's circle 1. We are done with the domain. Now let's go with circle 2, graph. All right, we got this. Okay, so what I did was I already inserted the graphing paper here. So let's take a look. So since the domain is set of all x values such that x is greater or equal to negative 3, if I were you, I'm going to start with x equals to negative 3. Because look at this right here, right? So the function is only defined from close negative 3 all the way up to infinity. So there is no graph on the left of negative 3. All right, but anyways, I'm just going to make a chart. So I'm going to have x. And then maybe I'll just write it as f of x equals square root of x plus 3. All right, so now let's take a look at this. So I'm going to start out with when x equals to negative 3. Now our f of negative 3 is going to be the square root of negative 3 plus 3, which is square root of 0, which is going to be 0. So this is telling you that when x is negative 3, y is 0. All right, now let's go with maybe x equals to negative 2, because negative 2 will be right here. Oops, that's a negative, sorry. All right, now if I plugged it in negative 2, we're going to have negative 2 plus 3 square rooted, which is square root of 1, which gives us 1. So here, in terms of an ordered pair, we can write this as negative 2 comma 1. All right, so now, well, who's next? Let me see, what is the nice number? If I plugged it in 0, right, do you see that we're going to have a square root of 3, which cannot be really simplified? You're going to have some crazy decimal values. So I'm going to skip when x equals to 0. How about x equals to 1? Because if so, then our square root becomes square root of 1 plus 3, which is square root of 4, which gives us a nice number as 2. So here we're going to have 1 comma 2. Oh, what the heck? Let's go one more. All right, now if I plug it in 4, we're going to have square root of 7. Okay, another crazy decimal value. Skip that. Now, what can I plug it in? What would be the next perfect square? How about 6? So if I plugged it in 6, right, here you're going to have 6 plus 3, which gives us square root of 9, which gives us 3. So here we're going to have 6 comma 3. I think that's good enough, so I'm just going to go with this. So let's plot negative 3 comma 1. So negative 3, oh sorry, negative 3 comma 0, sorry about that. Negative 3 comma 0, that will be here. And then negative 2 comma 1. And then 1 comma 2. Then 6 comma 3. 1, 2, 3, 4, 5, 6 comma to 3. All right, looking good. So our graph is going to look something like this. So the tail end of the graph keeps going up and up and up towards infinity. Although that the way I drew looks like it's going to drip down, but it's not. It's still going to keep going up and towards infinity. Now, to find the range of the function, what we need to do is you're going to have to view the graph bottom upward. Okay, so if I look at the graph from bottom upward, graph starts from where? Well, graph starts from negative 3 comma 0. So what's the y value? What's the starting y value? Well, starting y value is 0. And then where does the graph go? So remember, the tail end of our graph is, believe it or not, it's going to keep going up and up and up and up and towards infinity, like I said. Very slowly, but it's going towards infinity. So eventually, the tail end of the graph is going to go towards positive infinity. So our range, so let me just write down here, our range of f is nothing but starting from y equals to 0. So in this case, we're going to have to say settable y value, because range is settable y values, such that all the y value starts from 0 and it's going to go up to infinity. So that's the same thing as y is greater or equal to 0. Or another word, it's going to start from 0 and then this graph's going to shoot up to, very slowly, but towards positive infinity. So this is going to be that answer. I'm just going to box the interval notation here. Let's do another one. So we're going to do the same thing, but our function g of x now becomes cube root of x minus 2. Find the domain, graph, find the range. All right, so now let's first go with the domain. Look, we should be super happy because we're given the cube root, which is the odd root. So there's nothing for us to do. Domain is nothing but all real numbers. All real numbers. And interval notation will be negative infinity all the way up to positive infinity. Now to graph this, let me just bust out the graphing paper. And let's make the chart. Now in this case, domain is all real numbers, so that means that we can plug it in any value of x that we want. So here, our this is going to be the value of x, and g of x is cube root of x minus 2. All right, so let's start from the negative values for x, and then let's go towards the positive. All right, so let me see. What number should we pick? Maybe, what are we given here? Negative 1, 2, 3, 4, 5, 6, 7, 8. All right, so now let's take a look. So let's plug it in. Maybe x equals to negative 6. Do you see why I chose negative 6 for x? Because look, then inside of the cube root, I'm going to have negative 8. And negative 8, we can make that into a perfect cube. So that's why I chose x equals to negative 6. But anyway, so here you're going to have a cube root of negative 6 minus 2, which is cube root of negative 8. So what is that? negative 2. So here we're going to have negative 6 comma negative 2 as a point on the graph. All right, next point. If I plugged it in negative 5, you're going to have a cube root of negative 7. Ugly. All right, so what can I do here? How about let's jump and then plug it in when x equals to 1. So when x equals to 1, we're going to have a cube root of 1 minus 2, which is the cube root of negative 1, which gives us negative 1. So we need to plot 1 comma negative 1. Now let's plug it in 2. When x equals to 2, we get cube root of 2 minus 2, which is cube root of 0, which is going to give us 0. So we can plot 2 comma 0 on the graphing paper. Then what about 3? I think that's going to work out nicely as well. We got cube root of 3 minus 2, which is cube root of 1, which is 1. 3 comma 1. Now what can we plug it in? If I plugged it in 4, we're going to have cube root of 2. Bleh. All right, now what about 5? We get cube root of 3. No, that doesn't work. How about we skip it to when x equals to maybe 10? I think that's going to work out nicely because look, cube root of 10 minus 2 gives us the cube root of 8, which is going to be 2. So I'm going to plot 10 comma 2. All right, I'm just going to plot these points and see where it's going to take me. So let's do it. So we got negative 6 comma negative 2. 2, 3, 4, 5, 6. So this is negative 6 comma negative 2. All right, 1 comma negative 1. So this is 1, negative 1, 2 comma 0. And then 3 comma 1, 3 comma 1, 10 comma 2. 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 comma 2. All right, let me do the best I can to draw this graph. Oh my gosh. It's gonna look something like this. You know what? This is actually pretty darn good. All right, so here we go. So please note that this tail end of the graph, I know it's growing so slowly, but eventually it's gonna shoot towards infinity. And this tail end right here, I know the way I drew it, it's kind of ugly, but this is it's gonna go towards negative infinity eventually. Now let's go with the range. Again, a range is settable y values where the function is defined. So like I just said that the tail end of the graph on the left hand side of it, it's gonna go towards negative infinity. It's gonna shoot down eventually. Very slowly, but eventually. And the right hand side, that tail end of the graph eventually gonna go towards positive infinity. So when you look at the graph bottom upward like this, right? Remember, this tail end is gonna keep going down and down and down and down towards negative infinity now. So our starting quote unquote point would be negative infinity. Now let's look at the other tail end. So I know that this graph is moving really, really slow, but eventually this is going to go towards the positive infinity. So the end quote unquote point is going to be positive infinity. I said quote unquote. So those of you who's going to be taking calculus, we don't consider infinity as a number. So that's why I said quote unquote infinity as a point. But anyways, so here's the range. So that means what? If you're given the cube root, fifth root, or odd root, your domain is always going to be all real numbers. And then as you will see that the range is also going to be all real numbers regardless. All right, I'm gonna stop here, and I'm hoping that you are becoming one with radicals. But anyways, if you have any questions, please let me know. And great job once again, and I'll be talking to you soon. Bye.